In this video, we're going to talk about subspaces. Okay, so subspaces, just on a basic level, are subsets of some vector space V. So if I were to draw a picture, like imagine this circle represents V, some vector space. A subspace is something inside of that. Maybe it's the whole thing, maybe it's just part of it, but let's just call this subset H. So it's a subset of V that satisfies all the properties that the vector space does, so all 10 of those properties. But it turns out if you want to show something like a subset of a vector space satisfies all of those properties, you only really need to check 3 because the other 7 are satisfied automatically. And we call these things, these subsets, that satisfy all those properties of a vector space, subspaces. Okay, so what are those 3 properties that we need to check? Well, we need to check that the 0 vector of the vector space V is also in that subset H. We also have to check to see if it's closed under vector addition, which means anytime U and V are in H, then when we add them together to get U plus V, that needs to still be in H. And then it also needs to be closed under scalar multiplication. So if U is in H and C is a scalar, so a real number, then when we multiply U by C, that is also still in H. And it turns out that if our subset H satisfies these 3 properties, it automatically satisfies all 10 of them. So when that happens, we call this thing a subspace. So there are 2 key things that I want to note about subspaces before I do an example. So the first is that a subspace H of a vector space V is itself a vector space. I sort of mentioned that earlier. It's going to automatically satisfy all 10 of those properties when I check that those first 3 that I mentioned are true. And the second property is that V is a subspace of itself. So V is a subspace of V. And that we'd kind of expect to be true. Okay, so let's do an example. So let's let V be a vector space. I want to show that the set that only contains the 0 element, or the 0 vector, is a subspace of V. Okay, so how do we do this? So let's talk about the solution. So to show this, to show something is a subspace, I need to show that it satisfies those 3 properties. So the first property is that 0 needs to be in H. Okay, so H is my set here. In this case, H is this set that only contains 0 in it. Okay, and I'm going to put a question mark at the end of this because I don't necessarily know that this is true yet. So is 0 in H? Usually this is the easiest one to check. So I just look at my set, and is 0 in there? Well, yeah, it's in there. So yes, one of the elements in my set is 0. 0 is in our set. Okay, so that one's true pretty quickly. So 0 is in H. Awesome. Okay, so next, let's check to see if it's closed under addition. Closed under addition. And question mark again, because I don't know that this is true yet. Okay, so to do that, to check this, what I need to do is I need to take 2 things in H, take 2 elements of H. So I'm going to call them U and V. So I'm going to let U and V be in H. And then when I add them together, I need to check to see if that's still in H. But the only things that are in H are 0. So if U and V are in H, this means U and V both have to be 0. There's no other choice. And if they're both 0, now let's go ahead and add them together and get U plus V. Well, that's just going to be 0 plus 0. But 0 plus 0 equals 0. So the result of adding U and V together gives me 0. And that is definitely in H. The 0 vector is in H. Okay, so this checks off that it's closed under addition. Anytime I take 2 elements in H and I add them together to form U plus V, the result ended up being in H. So it's closed under addition. Okay, so I still have to check my third property, which is closure under scalar multiplication. Is it closed under scalar multiplication? And I'll put a question mark on this because I don't know if this is true yet. I need to check it. Okay, so for this, I'm going to begin by letting U be in my set. and C be a scalar. So it's got to be a real number. Then the only thing that's in H is 0. So U has to be 0. And if U is 0, that means when we multiply C times U, we get C times 0, because U, remember, U is 0. And then C times 0 equals 0, and the 0 vector is in H. Okay, so to recap, when we take an element U in H, and we multiply it by some scalar C, that result, C times U, is going to be in H, because it ended up being the 0 vector, and the 0 vector was in H. Okay, so at this point we have checked off, let's go ahead and check this one off. We've checked off all three of these properties. When all of the properties for something to be a subspace are true, that means it is a subspace. So therefore, our set just had the 0 vector in it, is a subspace of V, whatever the larger vector space was. So what this example shows is, no matter what our vector space is, if we just take the subset that has the 0 element in it, or the 0 vector in it, that is always going to be a subspace of the original vector space V. Okay, so let's do another example. So let's let V1 and V2 be elements of V, whatever our vector space is. And let's show that when we take the span of V1 and V2, that span is going to be a subspace of V. Okay. So let's talk about the solution to this. Alright, so I need to check those three properties again. So it's asking me to show that this thing is a subspace. So the first thing I need to do is, well, maybe let me call this set H. And so I need to check, well, is the 0 vector in H? So it's a 0 vector in H. And the answer to that is yes. Yes, it is. Well, for something to be in H, it's got to be in the span of these two vectors. So in the case of 0, I can write 0 as a linear combination of V1 and V2. So notice I'm forming a linear combination. And now let's think about, well, what goes in these two parentheses as the weights so that this linear combination becomes 0? Well, the simplest thing I could put in there is just 0 and 0. And that definitely is going to be equal to 0. So what this shows is that 0 is in the span of V1 and V2, which means 0 is in H. So the first property is true. Now let's check to see if it's closed under addition. So let's check closure under vector addition. Okay. And also notice that I'm saying vector here just because I'm using vector notation. But like we saw in the last video, sometimes we'll be working with different objects, like polynomials. And then we're not talking about vector addition, we're talking about polynomial addition. It just depends on what our objects are. Okay, so closure under vector addition. So why is this true? So let's let U and V both be in our set, in the span. So if U is in the set, that means U is a linear combination of V1 and V2. So maybe U is something like C1 times the first vector plus C2 times the second vector. So I'm letting U be in the span. And let's let V be in the span. So V is going to be a linear combination of them. So let's write D1 times V1 plus D2 times the second vector. So we've just written that U and V are linear combinations of V1 and V2. That's what it means for them to be in the span. So then, when we add them together and form U plus V. So if we add them together, what I'm going to do is, I'm going to factor out the terms that have V1 in common. Those are these two. And if I do that, I get C1 plus D1 times V1. And now I'm going to do the same thing with the terms that have V2 in common. If I factor out the V2, the coefficient is C2 plus D2. Okay, so U plus V is still a linear combination of V1 and V2. And the weights are this guy and this person over here, C2 plus D2. Okay, so this is in the span of v1 and v2 because it's a linear combination of v1 and v2. That means closure under vector addition is satisfied. So there's one more property for us to check, which is closure under scalar multiplication. Closure under scalar multiplication. And again, maybe I should have written a question mark over here. Question mark over here. That's just to remind myself, oh, I need to check this. I don't know if this is true yet until I show it's true. Okay, so for closure under scalar multiplication, so I need to take one vector in my set. So I'll let u be in my set. So if u is in this span, that means u can be written as c1 times v1 plus c2 times v2. So that's what it means for u to be in the span. And let's let c be a scalar, so c is going to be a real number. So then, when I multiply c times u, well, I get c times c1 times v1 plus c2 times v2. And now I can go ahead and distribute the c in. So I get c times c1 times the vector v1. And I'm going to put a parentheses around the scalar portion, c times c1. And then I'll get c times c2 times the vector v2. Okay, so when I took a vector u that was in my set in H, and I multiplied it by a scalar c, what I got was something times v1 plus something times v2. In other words, a linear combination of v1 and v2. So that means that this thing is in the span of v1 and v2 because it's a linear combination of it. Okay, so that means this third property is true. And at this point, we've checked all the properties for this thing to be a subspace. Okay, so I just kind of readjusted it to give myself a little bit of room here. So because it satisfies all three of these properties, therefore, our set span of v1, sorry, I have to kind of cram it in here a little bit, v1 and v2 is indeed a subspace of whatever vector space v we were talking about. Okay, so it turns out that if I form a span of even more elements, that it's still going to be a subspace, and that's this next theorem I'm about to state. So this theorem says if v1 all the way up until vp are elements of v, our vector space, then when we take the span of those vectors, v1 up to vp, that is going to be a subspace of v. And the proof is virtually identical to what we did up here, really, really similar. But I think conceptually it's easier to see with this example that we did with just the two vectors. Okay, so let's do another example. Okay, so in this next example, we have this set H, which is the set of vectors that have these things as the entries. Okay, and then I write this vertical line in set notation. This vertical line means such that. So in the last video, we saw another notation for such that, and that was writing a colon. Colon also meant such that. But writing a vertical line, kind of like one absolute value bar, also means such that in set notation. So I want to show you guys both notations, just in case you guys see it in the homework, so you know what it means. Okay, so then the question is H a subspace of R3? Okay, so let's talk about how to do this. So the idea that I'm going to use is the vectors in my set look like b minus 3c, and then I have a plus 4b, and then we have 2a minus 3b plus 5c. It turns out that I can write these, I can sort of split this up. Okay, so I can actually split this up as a linear combination of vectors. What I'm going to do is, and we've seen this before when we've written the general solution to systems of linear equations in parametric vector form, I can sort of write one vector that has all the a terms in it, so I sort of factor the a out. And the coefficients of a, in the first entry there's nothing, so 0. And the next entry there's 1, because it's just a. And the next entry is the 2, because I have 2a. And then plus a vector that has all the coefficients of b, so b factored out, and then the coefficients of b would be So the first entry it's 1, the next entry it's a 4, the third entry it's a -3. Those are the coefficients of B. And then I'd have a vector that represents all of the C terms. So when I factor that C out, the coefficients that are left over are, we got -3 for the first entry, 0 for the next one, and then for the third entry we have 5. Okay, so what we've just observed here is the set of vectors that look like this can always be written as a linear combination of these three vectors, like 0, 1, 2, 1, 4, -3, and then -3, 0, 5. So what that means is our set H is the span of these three vectors. It's the span of the vector 0, 1, 2, and the vector 1, 4, -3, and the vector -3, 0, 5. That's what H is. And we just showed in the previous theorem that when we take a bunch of vectors that are in a vector space, in this case we're taking vectors in R3, which is a vector space, then the span of those vectors is a subspace. So the span of these vectors is a subspace of R3 by the previous theorem. Okay, so that's kind of nice. It's nice that we had that theorem because it gave me a shortcut. I didn't have to verify the three properties. It was good enough to show that this vector, the set of vectors in this set are the span of these three vectors. I could write it as the span of a set of vectors. Okay, so I'm going to end this video with a conceptual observation about subspaces. So conceptually, a subspace H, or this is also true by vector spaces, but I'll just talk about it in the context of subspaces. A subspace H is a set that does two things. It has to contain 0, and any linear combination that I form using the things in H, using the elements in H, will still be in H. So if I take two things in H and I add them together, or I form some more complicated linear combination of them, it's still going to be in H. If I take an element in H and I scale it by something, it's still going to be in H. So conceptually, we need these two things to be true about H for it to be a subspace.